So it's been a while since my first video, and it's the delay was caused by my MSc project and also me moving places. So I think now I've settled in, and it's a good time to start the series on group theory. So again, I mentioned this in the first video, but I would recommend people watching this to have at least some background in classical mechanics, as in the Lagrangian and Hamiltonian formulations, and also some background in quantum mechanics, at least quantum mechanics one. And A linear algebra background would be essential as well. But I'll try to make this series as self-contained as possible. So even if you're a bit rusty, you can catch up. So I think without any delay, we should get into the subject matter. So I'll be using my notes, and yeah, let's get started. So today's, lecture will be more of an overview on symmetries and classical mechanics and how they're tied together. So let's begin. Let's start. So let me start sharing, and okay. Think yeah. Okay. So start with group theory. Symmetries. Okay. So when we start with group theory, if we were to talk about it in an introductory fashion, I would say all of physical group theory, that's group theory applied to physics, rests around one theorem. That's Noether's theorem. And we'll talk about Noether's theorem more in detail later. But uh, if I were to say what is the crux of Noether's theorem, it says that every symmetry in nature corresponds to a conservation law. So I mean, we have all heard of conservation of energy, conservation of momentum, conservation of angular momentum. All these conservation laws have an underlying symmetry behind them, and that gives rise to the conservation of these quantities. Okay, so that's Noether's theorem that symmetries to conservation laws. Okay. Now, apart from that, I think it's a good time to start actually with a review of classical mechanics, as I said, and work our way from the Newtonian formulation to the Lagrangian formulation, the Hamiltonian formulation, and establish what the action does and how it's critical in our understanding of the symmetries of classical mechanics. So I would say a good thing would be to derive Newton's second law from the action. Okay. So again, I would say people should have a background in classical mechanics to understand this thoroughly. But I'll just repeat a few things in the beginning. So let's derive Newton's second law from the action principle. Okay. So we know that action S is nothing but the integral of the Lagrangian dt. So we are integrating the Lagrangian over the variable of time. So small bits of time, that's dt. Now, if I were to write this, the action is a functional. So I would say it's a function of a function. So I can write the action as, again, for consistency, I'm looking at my notes. So notations stay the same. D0, D1, L of x dot dt. Now, x is your position, and x dot is an analog to velocity. And again, I'm saying analog to velocity because it's the generalized velocity. Now, so this is the definition of my action. Now, what would happen if I vary the action, if I introduce a small wiggle in the action, if I change it a little? So there, my notation becomes something like this. I have delta S integral of d naught d1. Okay, so what have I done over here? I've said that a small variation, a small change in action would look something like this, delta S. So it's basically, I'm just introducing that change on both sides of the equation. So delta S is that small change. Now, what is that small change? Again, small change is nothing but our Lagrangian is being changed with respect to both its parameters. So our Lagrangian is dependent on x and x dot, so we'll have to make the change with respect to both. So again, partial L by partial x, delta x is the change with respect to the variable x, and partial L by partial x dot is the change with respect to x dot. And if you think about it, I'm not actually changing anything over here. Dimensionally, it is still the same. Technically, if we were to, be physicists and not be as pedantic as mathematicians, this term over here and this term over here are technically the same thing. This term over here and this term over here are technically again the same thing. So I mean, my action is still delta S is nothing but it's delta L dt. I mean, this is mathematically wrong what I've written, but I've just written it to explain the meaning. So I'm just writing this part to again be mathematically precise. Okay, so we once we have this, we can start gerrymandering the equation a little bit. So if we look at this term over here, this the second one, this part over here, we can actually looking at okay, this integral over here actually looks suspiciously similar to something else. We can modify this to get what we want. See, at the end, we want Newton's second law. So we're trying to work our way to Newton's second law from the action. So what looks like this? I can say this is nothing but because I had delta x dot, which was the time derivative of delta x. So I can just write d by dt of delta x, which is again the time derivative of delta x. Now, if we take this, we can integrate by parts. I can say this is u and this is dv. So integrating by parts, u dv is equal to uv minus integral of v du, as far as I remember, best of my knowledge. And dot x equal to okay. So we've got this. Now, this again ties in to the principle of least action, that this term over here, by applying boundary conditions, vanishes. This goes to zero. So what like the best I can explain in a short time is that this term does not actually record a change. But I would say if you're unsure about this, just go back to classical mechanics and brush up a bit. But this goes to zero, so we have this term left, and we finally get delta S is T0 to T1 delta L x dot. Okay, so removing this, we've arrived at this term over here. Now, from this, it's not hard to spot the Euler-Lagrange equation. So from this, we can actually directly get what we want. Again, I'm not doing classical mechanics over here, so I won't be very thorough with uh, the introduction to classical mechanics, but just doing it as a review. So here we have the Euler-Lagrange equations. So the first step of our process is over. We have got the Euler-Lagrange equations from the action principle. Now we need to get Newton's second law from these equations. Again, not a very big ask. So we already have the Lagrange equations. Now all what we need to do is we need to write the Lagrangian in its definition. So its definition is the I mean it's I mean the L I mean the definition of Lagrangian is T minus V, which is the kinetic minus the potential energy, and we can just write that as half mx squared minus V of x. So again, my Lagrangian depends on x and x dot. So is equal to half m x dot squared minus v of x. Okay, so I have my Lagrangian written. Now I can take the partial derivative of the Lagrangian with respect to x, and I will get and okay. So we are over here. Now, again, this is starting to look familiar. This looks familiar. This looks familiar, but it's still not in its final form. So I can then write d by dt of mx dot plus v by x is equal to 0, which gives rise to f equals mx double dot. So we have arrived at Newton's second law. So again, the point of this, brief introduction was not to replace a full classical mechanics course, but it was just to uh, plug the gap. So I think since we have arrived at Newton's second law, and how the action is in a sense fundamental to symmetries, we have shown that the action, the and Newton's laws and the Lagrangian formulation are not all distinct. They're all related. So I think this is a good point to now kind of derive, a, I would say, the Hamiltonian formalism with the Beltrami identity. And this is again a review of classical mechanics. So I'll be brief about it. So let's take our Lagrangian. We have our Lagrangian and x and x dot. We have a Lagrangian, and we can take the derivative of the Lagrangian with respect to time. Okay, now I can write this as the partial derivative of the Lagrangian with respect to x. Now, why have I done this? I've done this because if I can see in my Lagrangian, there is no direct relation to time. It depends on x and x dot. So I can't just directly take the time derivative, without, using the variables which it is related to. So I've just expanded the relation to make it, mathematically consistent. Now, once we have this, we can write. Oh, sorry. Once we have this, we can write the L by dt as d by dt of del L dot dx. Okay. So again, over here, it's just manipulation. And then now, this looks very familiar to something called the Beltrami identity. So I'll write the Beltrami identity over here. T of Beltrami identity. Now, from this, I can get my Hamiltonian L and now obviously if I were to derive it completely, I would use like the Legendre transformations, but we are just doing a brief overview. So yes, this is our Hamiltonian. So, over the last 10 or so minutes, we have linked the action, the Lagrangian, Newton's second law, and now the Hamiltonian. So, we've covered all of classical mechanics. So, you might be asking, where's group theory in this? Yeah, we'll get to group theory, but this was important to kind of build up the basics because we might need these tools later on. So, yeah, we're done with the classical mechanics portion. Now let's get into actual group theory. So, okay, Noether's theorem. So, uh, let's write down Noether's theorem. Okay, now what does Noether's theorem actually state? Well, it states that wherever there's a symmetry in the system, there has to be a conservation law. So let's take any quantity which is conserved, angular momentum. Now, if I would just think about angular momentum being conserved, by the very notion of it being conserved, I should be able to infer that there is some symmetry in the system where angular momentum is being conserved. Similarly, the conservation of linear momentum, there should be some symmetry because of which linear momentum is being conserved. And the same is true with energy and any other physical quantity. So, in our discussion, like currently, we'll need three quantities: energy, momentum, and angular momentum. So, these are the three basic quantities which we always talk about in physics. And to know their symmetries is fundamental, is essential to doing physics properly. So, let's write out what each symmetry corresponds to, and how each conservation law has a symmetry behind it. Let's start with energy. Okay. Energy relates to time translational symmetry. So, in any system where there's a time translational symmetry, that is, if my system behaves the same way forward and backward, as in, if I were to shoot a video of the system and then rewind the video, if the system were to behave in the same way forwards and backwards, that's something called time translational symmetry. If the symmetry is obeyed, energy is conserved. So again, I reiterate, time translational symmetry is the symmetry of systems behaving in the same way when played forward and backward in time. So if they behave the same way, there's a symmetry. That symmetry is time translational symmetry. And if the symmetry is obeyed, we get the conservation of energy. So that's our first conservation law, conservation of energy. Second, linear momentum. This corresponds to translational symmetry. Now, it sounds similar, but there's a word missing. Time is missing from this. So, what does translational symmetry mean? So, if I were to move, forward in let's say the x direction, and if I were to perform an experiment at x equals 2 and x equals 5, and if the results of the experiment are the same, that means with respect to translation on the x-axis, there is a symmetry. My physics doesn't change with respect to motion along the x-axis. So there is a translational symmetry, and the conservation law, which is born out of that symmetry, is the conservation of linear momentum. Now, the last one, angular momentum, the juicy one. Angular momentum is conserved when there is a rotational symmetry. Okay, what does this mean? So if I were to perform an experiment facing the camera and I get some results, and if I were to turn back and perform the experiment over here and get the same results, that means the system over here has a rotational symmetry. I can rotate and I can get the same results. The rotation gives rise to, the rotational symmetry gives rise to the conservation of angular momentum. So that's the third fundamental symmetry which we talk about often in physics. So I would say this should be enough for the first lecture. In the next lecture, we should gloss over some details of the Noether charge, and actually investigating how there is a Noether current with respect to the Hamiltonian and the Lagrangian and the action, and how it plays out analytically when we actually solve equations. So I think this is enough for the first class, and I hope it was useful. Thank you.